Hey guys, welcome back to my channel. Today we're going to be solving an integral by linear algebra again, and I call this integral the 1, 2, 3 integral. Okay, so our first step is to factor the denominator right here, and we want to do that to go ahead and find our basis vectors. Okay, so let's factor the denominator. We can turn this into a cubic polynomial, and we just have to find the roots. Okay, so if you use the rational root theorem, we get the possible roots plus or minus 1, plus or minus 2, plus or minus 3, and plus or plus or minus 6. So they're the possible roots, and we just get that by factoring 6 divided by 1. Okay? So let's check them. Okay, let's see if positive 1 works. Positive 1 does not work since, they're all pluses. There's no way a bunch of positives can be 0. Let's try negative 1. Let's see. Minus 1, 5. Okay, minus 1 works. So a possible root is minus 1. That's alright. Okay. Okay, now we know positive 2 is out, since remember the positive. Let's try negative 2. Okay, it looks like negative 2 is in if we just check it. Let's try positive 3 is out, negative 3. And also negative 3. Okay, let's try negative 6. Okay, negative 6 does not work. Okay, so we get, these are the roots, so we just type, right, what? X minus negative 1, x minus negative 2, and x minus negative 3. The next step is to find our basis, alright? We went ahead and factored it. Okay, let's think about it. What can we put in the numerator instead of 3x squared plus 2x plus 11? Well, wouldn't it be nice if we had x plus 1 and x plus 2 on the top, so we could just cancel these out, okay, and get the integral, see if I'm on camera, of dx over x plus 3, okay? That would be nice, right? And then we know that this is going to be ln of absolute value of x plus 3, like that, right? Oops. Like that. And similarly, if you put x plus 1 and x plus 3 instead of x plus 1 and x plus 2, the x plus 1 and x plus 3 cancel, and we're left with 1 over x plus 2, which will be ln of x plus 2. Okay? And similarly to these two, we can also get ln of x plus 1. So I'm just going to put that right here. Okay? Okay, so did you know? Okay, notice. These three right here are all linearly independent, okay, and them combined make up the original, okay. So these are our bases. Okay, so now that we have our base vectors and they're all linearly independent, we can try and express our original integral as a linear combination of our basis vectors. Okay, so I've done that right here. Oh, I messed up here. This should be a 1. So I've done that right here, okay, and let's see what we can do. Okay, first of all, we can move this a to the inside, okay, and similar for everything else. Alright, next what can we do? We can differentiate both sides, okay, and you'll see why I'm doing this in a minute. So let's differentiate both sides, okay. Alright, so let's see. Differentiating an integral obviously does that, and differentiating multiple integrals are the same. So all of these go away. Okay, what do we get? We get 3x squared plus 12x plus 11 is equal to what? A plus b plus c. And then over each of them are over its own thing. So x plus 3, b over x plus 2, c over x plus 1. This entire thing over x, this entire thing. And the last time we ended up with this, I went ahead and multiplied both sides by x plus 1 times x plus 2 plus x times x plus 3. And all these cancel out, and then each one cancels out, but there's some things left, okay? So we get 3x cubed plus 12x plus 11 is equal to ax plus 1, just keep on going, right? Okay, we go ahead and expand all this out, and we get this. Notice the 3x squared matches up with the ax squared, bx squared, and cx squared. The 12x matches up with the 3ax, 5cx, and 4bx. And the 11 matches up with a 2a, 3b, and 6c. Okay. So because of how vectors work, if two vectors are equal, then each of their components are equal. So we know that 3x squared, we know that 3 is equal to a plus b plus c. Simple. Okay. 12 is equal to what? 3a plus 4b plus 5c. Not bad. 4, 5, 6, 3, 4, 5. Okay. And 11 is equal to 2a plus 3b plus 6c. 2a plus 3b plus 6c. We left off with this. Okay, so you can rewrite this as in the form like this, okay? So you have your 3, 12, 11 is equal to a, b, c times this matrix. You can rewrite it in the form a, x equals b, okay? And we could just solve it using x equal to a inverse times b. But I'm not actually going to solve it using row reduction or whatever. I'm actually just going to go ahead and solve it like you would normally using algebra. So yeah, I know that it's integration by linear algebra, but I'm not going to row reduce. You can row reduce. I'm leaving it to you guys. So because the video is getting a bit long, I'm just going to show you guys the work right here. I didn't make it all nice and neat. You can do it yourself, basically. It's not that difficult. And we basically get A is equal to B is equal to C, and they're all equal to 1. Okay? Alright. And now we just plug it in here. Okay? So here's the final thing. Let's erase all this work and do this. Be sure to pause the video and check my work if you want. And if you don't get something, pause it and look at it. Or try and do it yourself. Okay? What do we get? We get, as our final answer, ln of absolute value of x plus 1 plus ln of absolute value of x plus 2 plus, sorry about the noise, ln of absolute value of x plus 3. And then I'm going to just change the d to c. It's not the same c as this. I just don't want that. Okay, plus, oops. Hold on 1 second. Plus c. And there you go. That's what I call the 1, 2, 3 integral done by linear algebra. Okay, thanks for watching. It was a blast. Don't forget to try and do this try and do the row reduction by yourself, and also do the systems of equation by algebra by yourself. Just try it. And also try more rational integrals using linear algebra. Thank you for watching. Okay, one last thing. Sorry about all the weird sounds and stuff. My recording setup isn't the best. And also, if you have any tips on how I can make my videos better and more enjoyable, just tell me.